Welcome to part 2 of the Raymarching Shader in Unity tutorial by PeerPlay. In part 1 I've shown you an introduction to what a Raymarching Shader is. In this part we will start from scratch in a new Unity project to create the basic requirements of our shader. This contains a script to render the shader on the camera in screen space and create a camera frustum to get the correct ray directions in the shader. Creating these free tutorials takes a lot of time and effort, and I couldn't have created these without the support of all the amazing patrons at my Patreon. If you find the contents of my tutorials helpful, consider supporting me at Patreon. In doing so, you not only support me creating these, but you get access to the source files, exclusive tutorials and extra content. Special thanks to MR, Andrew Laboy, Devin the Dude, Derek Fegter and Patrick Nugent. We'll start in a new empty project in Unity. Let's right click in the assets, create and go to shader, and we're going to select the image effect shader because the Raymarching shader is actually an image effect shader in screen space. So click on that and we're going to call this the Raymarch shader. To apply this shader to the camera we need to have a C# script to do that. So let's create a new C# script and we're going to call this the Raymarch camera. Now let's go to the main camera and drag and drop the Raymarch camera onto the camera inspector. Now let's open up the Raymarch camera script in Visual Studio. Now the first thing that this script requires is to have a camera component, and otherwise this script won't work. So at the top of the class we're going to type require component, and we need to get the type of camera. The next thing we want is to execute this script in edit mode so that the Raymarch shader is always updated on the camera. So let's make another statement that we're going to execute this in edit mode. Now let's remove the update and the start function because we don't need them. Now for this script to work we need to make a reference to which shader we want to use this with. And for that we will make a private shader and we'll call this shader. And it's private so we don't see it in the inspector, but when we serialize this field we do. So let's serialize this field. Let me increase the font size a little bit more so you can read it a little bit better. Now we need to create a material based on the shader we select. Normally we would create a material in the void start, but we want this to run in edit mode. To solve this, we'll create a public and a private material. The public material will be set by a get if the private material hasn't been set and the shader slot isn't empty. So let's create a public material. And we'll call this material the Raymarch material. And in this material we'll use a get. Now let's also create a private material. And we'll call this the Raymarch mat. Now inside the public material Raymarch material we'll use a get. And we're going to return this material. So let's type return Raymarch mat. Now we only want to return this if this material hasn't been set and if this shader has been set. So let's create an if statement inside the get. If the Raymarch material hasn't been set and if the shader has been set, then we're going to say that the Raymarch material is a new material based on the shader. And to make sure that this material isn't going to be disposed by the garbage collection, we're also going to set the hide flags. So let's type the Raymarch material dot hide flags is going to be hide flags dot hide and unsave. Now let's get the camera component in a similar way. So we're going to type a public camera and we'll call this camera. And it's going to use a get. Now let's also create a private camera and we'll call this cam. Now let's write a get and we'll make an if statement in the get. If the cam is not being set yet, then we're going to say that the cam is going to be get component camera. And we'll then return the cam. Now let's write the unrender image to communicate with the shader. So we're going to type a void onRenderImage And this will autocomplete with a render texture source and a destination render texture. We'll start by making a check if the Raymarch material has been set. If it hasn't been set, we're just going to return the image. So we'll type an if statement. If the Raymarch material has not been set, with an exclamation mark, we're going to do a graphics.blit, and we'll blit from the source to the destination. And then we'll return. Now let's save the script and go back to Unity. In the inspector you can now see a slot for the shader, so let's select the Raymarch shader and drop that into this slot. Now let's open up the Raymarch shader. Now most of the variables in this standard image effect are already set up correctly. We're going to change just a few things. First of all, the hidden is going to be PeerPlay. Very important to change this, otherwise nothing will work. Now this shader doesn't have a pragma target, so we're going to change that, and we'll type pragma target is 3.0. To create a Raymarching shader, we need to get the origin position of the ray, which is the camera's world space position. In the on-render image, we'll send the camera position to a float 4 in this shader. So let's go to underneath the sampler to the main text, and we're going to write a uniform float 4, and we'll call this the cam world space. We also need a redirection based on the field of view and aspect ratio of the camera. In C#, we'll calculate for each corner of the screen a direction and send those directions in a matrix to the shader. So let's write a uniform float 4x4, and we'll call this the cam Frustum. Now the cam Frustum will be calculated in iSpace, and we need to convert that to world space, so we need one more float 4x4 to send to the shader. And that will be the cam2world transformation, which we can get directly from the camera. So we'll call this cam2world. Now let's just put these variables more to the top, so I'm going to copy them, remove them here, and put them here at the top. Now let's save the shader, and let's have a look at how we can create the camera Frustum. There are essentially two things we need to set. First of all, the camera Frustum, which consists out of 4 directions corresponding with the 4 corners of the screen. Secondly, we need to draw a quad on which we will render the output of the rays as a render texture. We need to make sure that all corners of the quad correspond with the correct Frustum corners. To create the Frustum matrix, we need to get the camera field of view and its aspect ratio. With these variables, we can calculate each corner. The first thing we need to do is to get the tangent of the field of view in radians divided by 2. We'll then create a vector to go up and go right. Notice that the go right vector also takes the aspect ratio into account. We then calculate each of the 4 corners of the Frustum. We start with the top left corner. First we move backwards, which is equal to minus vector 3.forward. Then we go left, this is equal to minus go right. And then we add the go up vector. Once we have all positions, we store them in a matrix. Now let's create the matrix in our Raymarch camera C# script. So let's go underneath the unrender image, and we're going to type a private matrix 4x4, and we'll call this cam Frustum. And as an input we'll get a camera, and we'll call that cam. Now we need to return a matrix, so let's create a temporary matrix in which we can set the variables. So let's type a matrix 4x4, and we'll call this the Frustum. And it's going to be a matrix 4x4.identity. And we're going to return the Frustum. Now we need to get the tangent of our field of view in radians. So let's create a float, and we'll call this FOV for field of view. And this is going to be a mathf.tangent. And first of all, we'll divide the cam field of view by 2. So let's type the cam.field of view, and we'll multiply this by 0.5f. Now the cam field of view is in degrees and we need to get radians. So we're going to multiply this by mathf.degree to radians. Now to get all four corners of our frustum, we'll create two vectors to say whether we go up or to go right. So let's create a vector 3 and we'll call this go up. And that is going to be a vector 3.up multiplied by the field of view. Now we also need a vector to go right, so let's create a vector 3 and we'll call this go right. And that is going to be vector 3.right multiplied by the field of view. And in the horizontal axis we'll also take into account the cam aspect ratio. So we'll multiply this by the cam.aspect. Now using these two vectors we can calculate the four corners of our frustum. So let's start with the top left corner. So we'll create a vector 3 and we'll call this the top left, TL. And we'll start by going backwards, so we'll do minus vector 3 dot forward. Now we need to go left, so we'll do a minus go right. So minus go right. And now we need to go up, so we'll do a plus go up. Let me copy this line and paste it here, and we'll make it a top right. And instead of minus go right, we'll use the plus go right. Now let's copy paste these lines again. Now this vector is going to be the bottom right. And this is going to be the bottom left. So to get the bottom right, we need to go right. So plus right and minus go up. And to get the bottom left, we need to go minus right and minus go up. Now we can apply the resulting vectors to our frustum matrix. So let's say frustum dot set row, and we're going to set row 0 to become the top left. Now in the on-render image we can set the matrix of the shader to this matrix. So let's write the Raymarch material dot set matrix. Now which matrix are we going to set? We'll set the cam frustum to become the cam frustum, and in here we'll get the camera. Now I made a little mistake. This shouldn't be the Raymarch map, but it should be the Raymarch material. So let's change that. Now let's also set the cam to world matrix of the shader and the camera world space. So we're going to talk to the Raymarch material again. We're going to set another matrix. And this matrix is called the cam to world matrix. And we're going to set this to the camera to world matrix. And we'll also set the camera world space vector. So let's talk again to the Raymarch material z vector. And we're going to set the vector that's called cam world space to become the camera transform position. We now need to draw the quad on which we will render the output of the shader. We will line the corners of the quad with the frustum we created. We're going to talk to the destination render texture. So we're going to type a render texture .active is the destination. We're going to push a quad into the text cohort 0 of the shader. And to do this, we're going to start with gl.pushMatrix. Now we're going to load the orthographic view, so gl.loadOrthographic. And let's set the pass of the Raymarch material to 0. So we're going to say Raymarch material.setPass to become 0. Now to start drawing our quad, we need to type gl.begin. And what are we going to begin? We're going to begin gl.quad. quads. We'll start with the bottom left position of the quad, and we'll start by writing to the text coord 0 slot in the shader, and we can do this with a multi-text coordinate 2. So we'll write gl.multi-text coordinate 2. Now the first variable is a unit. This will be just 0. And then we can specify an x and a y position, and the x and y position will be 0.0f and 0.0f, which is the bottom left corner. Now we also need to draw a vertex, so let's type gl.vertex3, and this will have the position of 0.0f, 0.0f, and the third one we don't really need because we are in orthographic view, so we don't need the z-axis, but we can use this z-axis to align this quad with the frustum. So let's look at the cam frustum. And if we look at the bottom left, then we can see that this is the third of the row of the matrix. So we're going to set this one to 3.0. Now let's duplicate this 3 times. This is going to be the bottom right. This is going to be the top right. And this is going to be the top left. For the bottom right, we're going to set the x value here to 1 and the x value here to 1, and this will become 2. Now to get the top right, we're going to set the x to 1 and the y to 1. And in the vertex, we're going to set the x to 1 and the y to 1, and this is going to be the index 1. And for the top left, we're going to set the x to 0 and the y to 1, and do the same in the vertex. And set the index to 0, which corresponds with the index of the matrix cam frustum. Now all that's left is to end this, so we'll say gl.end, and now we're going to pop the matrix. Now with this in place, let's save the C# script and let's go over to the shader. Now in the shader, in the v2 abstract, we're going to add a float3, and we'll call this ray, and this will use the text coordinate 1, and in this ray we will store the ray direction. Now in the vertex.c we have stored the index for our frustum matrix, and we want to get that index. So in the vertex we're gonna create a half, and we'll call this index. And that index is going to be the v.vertex.z. Now once we've set this index, we can set the v.vertex.z to 0. So v.vertex.z is going to be 0. Now we can set our ray to the corresponding cam frustum. And we'll say o.ray is going to be the cam frustum. And the index is going to be casted to an integer, and we'll get here the index. And as the matrix has 4 components, we only need to return the x, y, and z. So we'll do .x, y, and z. Now we'll normalize the ray in its z direction, so we'll say o.ray divided this by the absolute of the o.ray.z. Now we just need to convert the ray from I space to world space, and we can use the cam to world matrix to do this. So we'll say o.ray is multiply the cam to world matrix to o.ray. Now let's continue to the frag. Let's remove everything in the frag, and we're gonna set the ray direction. So let's create a float3, and we'll call this the ray direction, and that is going to be the normalize of the in.ray.xyz. Now we also need the ray origin, so we're going to say a float3, and that is going to be the ray origin, and the ray origin is the cam world space. Now these two variables, the ray direction and the ray origin, are needed in our sphere tracing, which we will do in the next part. For now, to test this out, we're going to return the ray direction as a color. So we're going to return a fixed 4, which contains the ray direction for its RG and B values, and a 1 there. Now let's save this shader and go back to Unity. And back in Unity, I find out that I made some mistakes, because this is not the result that I was looking for. So let's open up the Raymarching camera shader and let's look at what I did wrong. So let's scroll down, and if we look here, you can see that I've called this the Cam2World matrix. But the correct name is Cam2World. So let's copy that and paste that here. And the other mistake that I made is in assigning the rows to the frustum, because this one should be BR and the other one should be BL. So with that in place, let's save this script and go back to Unity. Now this is the result I was looking for. The camera will now render the ray directions as colors. If we change the field of view to a very low amount, you'll see that the colors will become more of the same because the directions are about the same. And the opposite is true for when we put the field of view very high. And the directions will also change by the aspect ratio. That's it for this part. In the next part we will use our ray direction and origin to write a distance estimator, sphere tracing, to calculate the distance from the camera to a distance field. For now, I want to thank you for following this tutorial part. If you found this tutorial helpful, feel free to like or share this video. If you want to stay updated to new release parts, subscribe to this channel. The source files of this part are available for patrons at my Patreon. Happy coding!